Let's check the operation of switch reluctance motor. Please observe the diagram here. The diagram shows the constructional details. So first we'll see the construction of switch reluctance motor, then followed by the operation or working of switch reluctance motor, and then torque speed characteristics. So at the very first instance, kindly observe that the switch reluctance motor, it consists of a stator having a set of coils represented as AA dash, BB dash, CC dash, DD dash. So these are like 4 pairs of coils forming 8 poles on the stator, and please notice that the rotor consists of 6 poles instead of 8, unlike the stator. Switch reluctance motor is known for providing high load, high torque to weight ratio compared to the other permanent magnet motors like a brushless DC motor, and it is already used in space applications because of its high torque to weight ratio. The main advantage of this motor compared to brushless DC motor is the absence of permanent magnet on the rotor. The rotor is simply made up of laminated soft iron core with no windings, just salient pole structure as indicated here. The stator consists of laminated iron core with multi-phase windings which are supplied from power converters or power electronic circuits. The stator windings must be energized in such a manner that unidirectional torque is developed on the rotor as a result of change in reluctance. The rotor position sensor provides necessary signal for deciding the switching sequence of the stator coils. In order to make the torque developed by the rotor to be smooth, more number of coils may be added to the stator, and the number of salient poles will often be too less for the rotor as compared to that of a stator. So the combination can be 8 pole stator and 6 pole rotor, or let us say 6 pole stator and 4 pole on rotor. Having understood the construction of switch reluctance motor, let us now take a look at the working of switch reluctance motor. Kindly observe the 2 diagrams indicated on the right hand side. They are shown here as figure A and figure B. In figure A, the magnetic flux has been shown produced by a coil labeled as A dash, or a pair of coils represented as coil A, and in the second diagram we see that the magnetic flux is produced by a pair of coils C by the stator, and this flux as produced by coil A is passing through the unaligned position of rotor poles. So also we observe that the number of poles on the stator are 6 while the number of poles on the rotor are 4. This mismatch in the numbers is mainly arranged in order to have sort of difference in the reluctance, so that whenever a pair of coil is energized, the torque can be produced. So in figure A, coil A is magnetized, exerting a clockwise force on the rotor. We observe that when coil A is energized, this pole is slightly unaligned, and when the flux is produced, you see the flux path is slightly, it is bent like this. But the magnetic lines of forces, they have a tendency to straighten up. So as they straighten up, in process of doing so, they exert a torque on the rotor, because rotor is free to move, stator is fixed, so rotor position changes and it tends to move like this here, and we observe that the rotor will rotate clockwise until these poles get aligned with the energized coil. but the rotor position sensors, they signal coil A to be switched off as soon as the alignment position is matched. But due to the momentum of the rotor will continue to move beyond the coil A, and in doing so we observe that the another pair of poles, they will come nearly in alignment with coil C this time, as shown in the diagram below. So the other two silent poles, they are now nearly in line with coil C. So the coil C will be energized, keeping rotor to turn smoothly in the same direction as earlier. So the correct turning on and turning off each of these coils in a sequence is very essential for the proper operation of switch reluctance motor. So this kind of switching can be done only when the rotor position is sensed by some kind of sensors like optical sensor or Hall effect sensor. But modern day drives which are coming with the switch reluctance motor, they tend to do away with the sensor, and simply by measuring the voltage and current waveforms, it is possible to obtain the rotor position without actually sensing them. Let us understand the torque speed characteristics of switch reluctance motor. The torque developed by the switch reluctance motor depends on the rotor advance angle or rotor position and rotor speed. So on the y-axis you observe that it is a torque along with current and advance angle theta, and on the x-axis you have the rotor angular speed. So there are three phases of these torque speed characteristics. So you can observe these three phases are represented as, first one is this one, when the speed is below the base speed, it is current chopping mode. Then from base speed to certain higher speed, it is a constant power mode. And lastly, this is a constant T omega square product mode. So initially in this region, the torque developed by the motor is constant while the speed is increasing. This mode is characterized by the limitation that we have to keep the maximum torque limited to the physical wear and tear on the motor, and so also to limit the starting current when the motor is operating. So when the speed is 0, a very high current might be drawn by the motor, and we would like to limit the starting torque to certain maximum value. So as the speed increases, the torque is maintained constant by keeping current constant, and so also the angle of advance, rotor angle of advance, where the coils are energized, that is also kept constant. So this mode where the current is essentially controlling the torque is called as a current chopping mode. Now above the base speed indicated by this omega base down here, above the base speed we don't want the torque to remain as it is, because as the speed of the motor increases, especially for the electric vehicle or traction applications, we want that the torque decreases with increase in speed, so that the amount of power drawn from the source does not exceed the limit. So the rotor advance angle will be increased. We increase the rotor advance angle in order to limit the torque while keeping the current constant. So above the base speed, the rotor advance angle is increased to a maximum value. So here we can see the rotor advance angle is increased. So this control is again all done with the help of a microcontroller, and we observe that during this stage the torque decreases while the speed is increasing, and product of torque and speed is the power, so power remains constant. Here this second phase of operation, it is called as a constant power mode or advance angle control mode, as that advance angle is increased to its maximum value. So this is the constant power mode. Beyond the specific value of speed as indicated here by the second reference line, the advance angle cannot be increased further. There is a limitation to that, and hence the current will start decreasing. Now beyond this we cannot control the current, maintain the current in the same value, so current start decreasing, and with decrease in current there is a further decline in the torque. So you can see there is a change in the slope of torque speed characteristics further as the speed increases. So this mode is known as a constant t omega square mode. So we see that the characteristics are as required for the operation of electric vehicle. Initially high torque, and then as the speed increases in two phases, the torque decreases with the increasing speed. Now let us study the control of switch reluctance motor. So SRM control methods. Mainly the control is focused towards controlling the torque corresponding to the speed of the motor using various control strategies. So we have already seen the torque speed characteristics of switch reluctance motor. Let us see how it is actually implemented using the block diagram and also using a circuit. Kindly observe here the block diagram indicates this switch reluctance motor here in the form of a block SRM. It is connected to the load. Load here means the electric vehicle that is to be driven for our case. And apart from the reluctance motor, we have got a power supply in the form of an inverter, which is again supplied from either from a battery or from a diode rectifier from some source. So this battery will give DC supply, and then the DC supply will be converted into multi-phase supply for the windings here. So it is like an inverter. Apart from that, there are several sensors here, okay, controller and the control commands. Control commands are in the form of the driver inputs in terms of accelerator, brake and other things. So let us observe here the conventional switch reluctance motor drive system consists of a switch reluctance motor, right, then a power inverter here, okay, then various sensors are there. So voltage sensor, current sensor, they are not indicated for the purpose of simplicity. Apart from voltage sensor, current sensor, there are position sensors. So voltage sensor is not shown, okay, and the control circuitry. So this control circuitry generally consists of a very advanced digital signal processor controllers, DSP controllers and its peripherals. The switch reluctance motor drive inverter, written here as a power converter, is connected to the DC supply, which can be derived from the utility lines or from a front end diode rectifier or maybe a battery, as in the case of electric vehicle. The controller provides the gating signal for operation of the inverters, because this inverter consists of transistor switches. As we have seen in the BLDC operation, there are several transistor switches which supply current to the stator coils, so they have to be switched, so they require gating signals, and those gating signals are as per the control strategy depending upon the speed and the mode of operation of the switch reluctance motor, while sensing the various signals, current, position, voltage and control commands. Let us observe the circuit. Kindly here at the bottom pay your attention that this is a 8-pole stator and 6-pole rotor type of switch reluctance motor, and it consists of a driver circuit. Right hand side, this is a DC single DC supply, right, and then this DC supply is connected to several sets of switches, like here SA1, SA1, SA2, then similarly SB1, SB2. So combination of switches, these switches, a pair of switch SA1, SA2, similarly SB1, SB2 and then SC1, SC2. These switches can provide bidirectional current to the coils. One pair of switches is there for one pair of coils. So there are 4 such pairs, A, B, C, D. So there are 8 poles, 4 pairs of coil. Now below the base speed, the back EMF is generally lower than the DC bus voltage. So back EMF is the EMF that is induced in the stator coil when the rotor operates and flux is induced. So when the speed is 0, back EMF 0, and maximum torque will be produced in this particular phase when the phases are turned on in the unaligned position. Okay, and as soon as the rotor rotates, the stator coil current is turned off for that corresponding winding in the aligned position. So the phase current is regulated by the PWM or pulse width modulation control. We will see the details of pulse width modulation control when we study the power electronic converter circuits. When the speed of the switch reluctance motor reaches the base speed, the back EMF becomes higher than the DC bus voltage. So in order to keep developing the torque and also the high current, the rotor advance angle is increased in order to have a proportionate torque available while the speed is increasing. And naturally the phases are usually excited ahead of the unaligned position, so slightly angle of advance is increased, and so that we keep getting the motor torque. Since EMF developed inside the motor is higher than the DC bus, so current should not stop. So in order to maintain this DC bus voltage higher, we increase the rotor angle in advance as explained earlier. Now regenerative braking can also be achieved in the switch reluctance motor by operating switch reluctance motor as a switch reluctance generator with stator excited near the rotor aligned position. So whenever the driver applies the brake or the electric vehicle is going downhill, so rotor position sensors can be programmed in such a manner whenever brakes are applied or there is no input from the accelerator. So the algorithm can be changed so that the coil can be excited at the aligned position instead of being unaligned position, and then turned off before the unaligned region is reached. So this way it is possible to recover some amount of energy back to the source, and this same circuit will be able to take the energy back and store the battery as a rechargeable battery. Recharging can be done for this battery.